So we're going to continue talking about probability. So just a quick little summary for our rules for having a probability space is that all probabilities are represented as a number between 0 and 1. The probability of the entire sample space of all possible outcomes needs to be 1. If we have equally outcomes, we can calculate a probability by just counting the number of outcomes divided by the total number of outcomes in our sample space. And then if we have a probability space, the complement rule should hold in that the probability of P of not A is 1 minus P of A. Everybody's okay? So just as a review, these are all things we've talked about already. When we have expected value, very much like we do with the expected counts, to find the expected value of something, it's just the probability of success times the total number of trials. So if you are flipping a fair coin 100 times, how many times would we expect to get tails? 50, right? A half times 100. Everybody's okay? Or if you're a 300 hitter in baseball and you get 1,000, have 1,000 at bats, you'd expect how many hits? 0.3 times 1,000, so 300. Everybody's okay with this? What if we flip the coin 25 times? How many times would we expect to get tails? 12.5. Does that expected value have to make sense in context of the problem? It does not. Think about it like the average American family has like 1.7 kids or something. Like nobody has 0.7 of a kid, but it's the expected, right? You're giggling because you're like, I know some kids that seem like 0.7s to me. That's rude, guys. Rude. All right. We talked about mutually exclusive events. Remember, mutually exclusive events are events that have no outcomes in common, or that is that the intersection of those two events is empty, or its probability is 0. So we said for mutually exclusive events, we can calculate probability of A or B as just the probability of A plus the probability of B. So what we talked about in 8.2 is ringing a bell. So again, just recapping. Quick example here. So suppose we chose a student at random to determine their gender and whether or not they have pierced ears. So find the probability that our student has pierced ears. What would that probability be? So 103 over 178. All of our pierced ear students divided by the total number of students. That's correct. What is the probability that we are male and pierced ears? 19 over 178. Very good. And what's the probability that we are male or pierced ears? So we need all of our ear pierced and all of our males, right? So 84 plus 19 plus 71. 174 is the answer. Yep, 174 out of 178. Or you could have done it as a complement, right? 1 minus not male and not ears pierced. So you could have had 178 minus 4 and also gotten 176 or 174 out of 178. Yeah, sure. So if we say that event A is being male and event B has pierced ears, we can translate this two-way table into a Venn diagram. Remember, we want to start by filling out the intersection first. So the probability of male and pierced ears is 19. Since I know that there's 90 total in our male circle, and we've already placed 19 in the intersection, the probability that we are male and don't have pierced ears, that's A intersect B complement, should be 71. And since we have 103 in our female circle, no, in our ears pierced circle, we know that, and we've already placed 19 of them, that means we have 84 here, which is not male and has pierced ears, or A complement intersect B. And then the 4 that are neither male nor have pierced ears are out here. That's A complement intersect B complement. So again, just looking at symbolically what parts of the Venn diagram the symbols apply to. Feels like that's helpful. Again, not unlike what we did in section 2, right? Or 1 and 2. We did Venn diagrams, I think, in both places. Okay. So what happens if I have two events that aren't necessarily mutually exclusive? So for example, if I'm talking about event A and then event B, if I count everything in event A, I count the intersection. And if I count everything in event B, I also count the intersection. We've double counted everything in the intersection, right? So if I want to count everything that's in the two sets, I can count everything in the yellow, everything in the blue, and then subtract the intersection once. Since I double counted it, if I subtract it one time, it'll turn into single counted. So this is our general formula for counting a union. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. And if our events happen to be mutually exclusive, this probability is 0. So it just turns into the previous formula, right? So this is like the master formula, the more general version. The mutually exclusive formula is like the specific version. Is everybody okay with this idea? I think we mentioned this last time also when we talked about mutually exclusive. Should ring a bell, right? I see one head shake, I'll take it. So this is exactly what I'm talking about here. So we had mutually exclusive. We have two events in general. Notice that the only difference is this minus the intersection piece. But in the mutually exclusive situation, that probability is 0 for the intersection. So they're the same formula. You guys see that? So in general, this is the only one that I bother memorizing because it works in every situation. This one only works in mutually exclusive. Cool? All right. So what about intersecting events? So if I have A and B, well, it kind of depends on whether the events are independent or not. By independent, I mean, does one event depend on the other? So if I say, what's the probability of flipping a coin and getting heads, and then flipping the coin again and getting heads a second time? Does the first coin flip affect the outcome of the second coin flip? No. So those events would be independent. It'd be the probability of the first coin flip, 1/2, times the probability of the second coin flip, 1/2. So 1/2 times 1/2 is 0.25. It's the probability of flipping heads 2 times in a row. How about I spin a roulette wheel? And I'm looking at the outcomes on a roulette wheel. Are those independent events? Yes. How about drawing a card from a deck of cards? Depends. So if I ask you to draw 2 cards from the deck, the first card is out of how many? 52. The second card is now out of how many? 51. The drawing of the first card has affected the probability of the second card. How could I make it so that they're independent? If I put the first card back. So with replacement and without replacement is often are going to be our verbal indicator whether something is independent or dependent. Does that feel okay? So if they are independent, we can just multiply them together, the two probabilities, all willy-nilly. Everybody's cool? Okay. All right. So again, with replacement, without replacement is often our indicator whether something is independent or dependent. So if you're drawing names out of a hat and you're putting the names back after you read them off, drawing names out of the hat is now an independent event. If you're drawing the names out of the hat and then keeping them out, this is now a dependent event, right? Because we're reducing the number of names in the hat each pull. So the outcome of the first pull is going to affect the previous pull. Is everybody okay with that idea? Okay. So for a quick example, say we have 5 green gummy bears and 4 red gummy bears. You've already picked out 1 green gummy bear. What's the probability that the second gummy bear will also be green if I'm not replacing gummy bears? So how many green gummy bears are left in the bag if I haven't replaced? 4. How many total gummy bears do I have? 8. So without replacement, the probability should be 4 out of 8, or 50%. What if I do replace? What would the probability be? 5 out of 9, or 0.55 repeating. Is everybody okay there? So keep in mind that mutually exclusive and independent are not related. You can be independent and not mutually exclusive. You can be mutually exclusive and dependent, or you can be dependent and not mutually exclusive. Like, any of those things can happen, right? So just for an example, let's say we're talking about flipping a coin twice. That's both mutually exclusive because the outcomes of our coin flip are either heads or tails. You can't be both heads and tails. And they're independent because the first coin flip doesn't affect the second coin flip. Is everybody okay? If we're drawing from a deck of cards and looking at their suits, this is mutually exclusive because you can't have one card that is 2 suits, right? You're either diamonds or spades or whatever. Like, you can't be both. But it's not independent because removing one card changes the probability in the deck, right? So if I want the same, if we're in a deck of cards, you pick one card, replace it, put it back, pick a second card, and you're comparing like types of cards and suits, you can get something that is like, say, a jack and a diamond. So those are not disjoint, right? You can have one card that's both a jack and a diamond. And that is now independent because you're putting cards back after you draw them, right? So we had both mutually exclusive but not independent. This is not mutually exclusive but still independent. Is everybody cool? That the two do not mean the same thing, and you can have one without the other, or both happening at the same time, or neither happening at the same time. All right, let's take a look at a numeric example here. We've collected the distribution of blood types in 3 different countries. So the distribution of blood types in the US, in China, and Russia is listed here. So my first question for you is, what is the probability of an AB type in the United States? How'd you get that so fast, Joey? They all have to add up to 1, right? 100% of our US people have to have a blood type. So I can just take 1 minus 0.43 minus 0.41 minus 0.12, and that should be 0.04. Probability of a type B in Russia, you do it the same way, right? I think it's 0.12. Oh, 0.18. Sorry. Yeah, of course. Because it ends in 2. 9 plus 9 plus 4 ends in 2. Oopsie daisy. All right. Next question. Dirk lives in the United States and has type B blood. Type B can only receive types O and B. What is the probability that a randomly chosen U.S. citizen can donate blood to Dirk? So the first thing I'd want to do is to recast this problem in a probability statement. So we're looking for the probability of someone being O or B. You guys agree? Are those, since it's a union event, we care only if those two events are mutually exclusive. Can someone be both type B and type O blood? No. So the probability of O or B is just the probability of O plus the probability of B. So that should be 0.55. Joey.
Why is it the minus
Because we said it was mutually exclusive, which says that probability of 0 is 0.
Oh.
Or you could just omit it. It's fine to omit it.
What if it wasn't mutually exclusive?
Then you'd need a different table to sort that out because you couldn't tell how many were in the intersection.
Okay.
It wouldn't be constructed this way. You'd have like a two-way table for each country or something. All right. What is the probability of randomly choosing a person from the U.S. with type O blood and then randomly choosing a person from China with type O blood? Is this an and or an or? And. So this is the probability of U.S. and O and probability of China and O. You guys agree? Okay. Since it's an and event, we care about whether it's independent or not. Is the blood type in U.S. affect the blood type in China? No. So these are independent events. So it's just going to be the probability of O in the U.S. times the probability of O in China. So 0.43 times 0.36, or a shade over 15%. Does that feel okay? So again, the big takeaway here on these story problems is the first step is I want to recast it as just some probability statement, right? So I can use my formulas. The big thing is deciding whether it's an and or an or there's a third choice coming up. Is everybody okay? Next one says, what is the probability of choosing 3 people, one from the US, one from China, and one from Russia, all with type O blood? So this would be and or an or. And. How many ands, though? Well, really 2, right? It's O in the US, and O in China, and O in Russia. So I said and twice, right? Yes. And since it's and events, we're not adding, right? And events, we care if it's independent. Blood type is independent from country. So we're just going to end up with the probability of O in the US times the probability of O in China times the probability of O in Russia, or shade over 6%. We haven't discussed how to do any dependent probabilities yet. We will, but it's coming. Again, don't know how to do it yet, but we'll get to it today. Deal? All right. The big takeaway here is that this and event It doesn't matter how many things you've ANDed together. If they're all independent, you just have like the product of these, right? If I flip a coin 10 times, what's the probability of getting 10 heads? Well, it's 0.5 times 0.5 times 0.5, and you do that 10 times, right? Multiply 0.5 by itself 10 times. So 0.5 to the 10th. So what is that? 1 out of 1024, I think. How's that for some mental math? All right. Part E says, what is the probability of randomly choosing 3 people, 1 from each country, all with the same type of blood? So this is both an or an and, right? You could have probability of all O's, or the probability of all A's, or the probability of all B's, or the probability of all AB's. Is everybody okay with that? Since these are all mutually exclusive events, I can just do the probability of all O plus the probability of all A plus the probability of all B plus the probability of all AB. Everybody's good with that so far? Probability of all O is an AND event, right? That's O in the US and O in China and O in Russia. Those are all independent events. So to calculate those, I'm just going to multiply them together. This is our answer from the previous one where we did just that. Probability of all A's is going to be the same idea. Multiply all of our A's together. For the same thing for our B's. And the same thing for AB's. Does that feel okay? And I add those all together. Shade over 10%. What do you guys think? Is that okay? So again, the hardest part about these questions is going to be decoding what to do. The actual arithmetic is really easy. All we're doing is like adding, subtracting, multiplying, dividing numbers. There's no like algebra to do. There's no like solving an equation. There's no like anything funky. But reading the question, understanding what is going on and how to write it as a probability statement, that's the hard part. Alyssa.
So you multiplied all like the values for O from all 3 countries and then all the ones from A and then B and A and I.
Correct. Everybody cool so far? All right. Another set of examples. It is estimated that 17% of all computers bought from a certain manufacturer require 1 repair job during the first month. That 7% will need 2 repair jobs during the first month, and 4% will require 3 or more repairs during the first month. What's the probability that a computer will need no repairs? Well, again, we want to rewrite this as a probability statement. So let's define some events here. So I'll say event A is 1 repair, event B is 2 repairs, and event C is 3 or more repairs. Everybody okay? So we know that for event A, the probability is 0.17, for B it's 0.07, and for C it's 0.04, right? So far so good? So I'm just going to kind of record that up here. What I want to do now is rewrite this as a probability statement. What is the probability the computer will need no repairs? So first thing I'm going to do is note that, is that events A, B, and C are mutually exclusive. You can't have 1 repair and also have 2 repairs. It's like an either or situation. So I know that we have a mutually exclusive events. So the probability of the entire sample space should equal 1, right? Everybody knows that. And the set of events in our sample space are 1 repair, 2 repair, 3 or more repairs. And what other event is missing? No repairs. So I can say that no repairs plus 1 repair plus 2 repair plus 3 or more repairs should equal 1. Or I can, if I rearrange that and I subtract those guys to the other side, fill in the values and subtract, 0.72 should be the probability of no repairs needed. Is everybody okay with that? How did I use the mutually exclusive property here to write this? So if I go all the way back to the beginning, we had P of S is equal to 1, right? That's a property for a probability space, where S is the sample space, right? The sample space is just the union of all possible outcomes. If all of our events are mutually exclusive, it's the union of all of our events is the same as the sample space, and that's why them being mutually exclusive mattered to me. Because if I just added up all the events, then I can do that because it's mutually exclusive for a union statement. Okay. What is the probability the computer will need no more than 1 repair? What does no more mean? 1 or less. So this would be the probability of 0 repairs or 1 repair. So because they're mutually exclusive, I just add them, 0.89. Cool. What is the probability the computer will need some repair? What do I mean by some repair? Right, at least once. So that could be the probability of you need to be repaired 1 time, 2 time, or 3 or more. So 0.28. What do you notice about this number and the previous number? Oh, never mind. I lied. It was the one before that. I don't really care. Alternatively, you could have done this with a complement rule as well. So you could do 1 minus the probability that we needed no repairs. Remember, that was the first thing we calculated. That was the 0.72. So you could have used your previous answer and the complement rule. Now, this is no big deal. But what if there's like 25 things that were not, and they were like, could occur in combination? It could get nasty. Complement rule is often real nice. All right, if you bought 2 computers from the manufacturer, what is the probability that neither one will require repair? So, is the repair of one computer independent from the repair of the other computer? Yeah, right, that doesn't affect one another. So, probability neither need repair is the probability of no repair and no repair. So we just multiply. The probability that we don't need to repair is 0.72. So almost 52%. Still feel okay? What's the probability that both will require some repair? So it's probability of repair and repair. So that was, again, some repair would be the 0.28 number, or you could do 1 minus no repair. Either is fine. Remember, we calculated some repair in a previous question. So almost 8%. All right, Joey, here's the answer to your question. What do we do if the events are not independent? So what we're going to do is define something called a conditional probability. So if we have one event that depends on a previous event, we call that probability conditional probability. And the way we're going to denote that is if I have event B depending on event A, we'd write that as the probability of event B given that event A has already occurred. Everybody's okay with that? So let's say that this is the probability of drawing a 4 from a standard deck of cards, given that we've already drawn the ace of spades. What is the probability? Well, 4, because there's 4 fours, right? 4 of ace, 4 diamonds, spades, hearts, and clubs. 4 out of 51. Very good. 4 because we have 4 fours. 51 because when we take the ace of spades out, there's only 51 cards remaining in our deck. Is everybody okay with that idea? So the formula to calculate this, sometimes we can just use our common sense, right? If we're talking about like a deck of cards or pulling gummy bears out of a bag or something, you can just common sense it out. That's fine. Other times you might need a formula. This is the technical formula for that conditional probability. It's the probability of A given B is equal to the probability of A and B divided by the probability of B. Note that if I switch the conditions for A and B, so if I want the probability of B given A, that's going to be the probability of B intersect A divided by the probability of A. But notice something here. What do you notice about the numerators of these two formulas? They're flipped. But what does that mean? It's still the same, right? Because we know, remember, the intersection is commutative, that A intersect B is the same as B intersect A. So the only thing that's really changing in our formula when we swap the conditionals is the denominator, right? So the condition is the denominator. Everybody cool? So that's just what I point out here in the last slide. Everybody happy so far? All right, so let's start doing some conditional probability calculation. All right, so we have a two-way table below. We're going to define the event E as a grade coming from engineering and physical sciences course, and the grade and L, the event L, as a grade lower than a B. So let's start by first finding the probability of getting, or of event L. What would that be? Well, to do that, we have to total some stuff up, right? So we need the number of grades lower than a B, so I need to total this column. Everybody agree? And then I need to divide it by the overall total. So let's total those guys out. So what would this probability be for L? Yep. Everybody happy there? So the next one, the probability of E given L. So again, according to our formula, that's the probability of E and L divided by the probability of L. So the probability of E and L is 800 over 10,000, right? Because E and L is here, 800. and to make it a probability, we divide it by all possible outcomes, 10,000. Divided by the probability of L, which was 3656 over 10,000. Notice the 10,000s can cancel, so you could just write it as 800 over 3656. Is everybody okay there? What if we flip them? What if it's L given E? Well, how many are in L? 3656. Oh, I'm sorry. In E, L and E is 800, right? Divided by the number in E, 1600, so 0.5. Is everybody okay? So notice when I'm given a two-way table like this, these formulas, instead of P's, could really be N's, just the number of things in the intersection divided by the number of things in B. If you're drawing this from a two-way table, you can ignore the probabilities and just count the numbers. Because this, for example, would have been 800 out of 10,000 divided by 1,600 out of 10,000. And the out of 10,000 just cancel. It's not wrong to include it, but that's what happened there. This is usually the easiest situation for a conditional probability, is when you have a two-way table. All right. So if I don't have independent events and I want to calculate A and B, it's going to be the probability of A times the probability of B given A. So let's say it's the probability of drawing a 4 from a standard deck of cards and drawing another 4 from a standard deck of cards. What's the probability of drawing a 4? Well, 4, right? 4 out of 52, because there's 4 of hearts, diamonds, spades, and clubs. And then how about, and then the probability of drawing a second 4 would be, we've taken 1 4 out, so how many 4s are left in there? 3. And how many total cards are left in there? 51. So it'd be 4 out of 52 times 3 out of 51. Does that feel okay? And sometimes that conditional probability is just that easy, right? If it's a simple situation, you don't need to use a formula to calculate it. You can just use common sense. And I want to just point out that this formula here is just a rearrangement of our conditional probability formula, right? If I took this formula and multiplied both sides by P of A, I'd get just this formula. You see that? All right. Another technique that's often helpful in dealing with a conditional probability situation, or many of these compound probability situations, is drawing a tree diagram. So I'm going to overkill it here for a simple situation. And then we'll do some other situations where it's a little bit more necessary to have the tree diagram. So let's say we're flipping a coin twice. And we want to find the probability of getting heads twice. I know, it's not that hard. So I will draw a tree diagram. So the first toss, I could get heads, or I could get tails. If I've gotten heads on my second toss, I could again get heads, or could get tails. Or if I'd gotten tails, I could get, on my second toss, I could get heads or tails. Since it's a fair coin and it's an independent event, the probability for every toss is 1/2. So if I want the probability of getting 2 heads in a row, I'm going down this path, right? Head, head. So I multiply 1/2 times 1/2. and I get 1/4. Everybody's okay there? What if I wanted the probability of getting a head and a tail? So I would, that's this path, and also, I should say, or also this path, right? So I would have 1/2 times 1/2 plus 1/2 times 1/2. So it's 0.5 still. Everybody's okay? All right. Let's look at another situation. So the Pew Internet and American Life Project finds 93% of teenagers use the internet. 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So I'm going to define some letters for our events. Oh, no, I'm not. I'm just going to draw the tree diagram, I guess. So either yes or no, we're online. If we're yes, we're 93%. How did I know that no would be 0.07? It's 1 minus 93%, right? Everybody's good? And then we know that if we're also made a profile, that's 0.55. How do I know that not making a profile is 0.45? Run minus 55, right? And then if we're not online, how did I know that making a profile was 0? You can't make a profile if you're not online, right? If you're not using the internet, then what are you going to make it with? Just post it on the side of your house or something? I don't know. It'd be a weird thing to do. And so no then is 100%, right? So if we're looking for online and posted a profile, we're looking for this path right here. So 0.93 times 0.55. Everybody's okay with that? What if I wanted teens that have not posted a profile? So I would do this path, haven't posted a profile, so 0.93 times 0.45, or this path, 0.07 times 0.1, and since it's an or, we add them up, right? Is that okay? So the tree diagram can be especially helpful for these or situations that are kind of tough to detect. In an experiment, researcher places 6 green toys and 4 red toys into a container. A child is asked to select 2 toys at random. What is the probability that the child selects 2 red toys? So make a tree diagram. Your first choice is either red or green. And then depending on that second choice, again, they can either be red or green. So we could have red, 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 green, green, red, green, green. Those are the 4 possible outcomes here. Everybody's good? So the probability of getting a red on our first choice would be, we have 4 red toys and 6 green toys, so it'd be 4 out of 10. And then green would be 6 out of 10. How about our second red, given that we've already chosen a red? 3 out of 9. And green would be 6 out of 9, because we took a red toy out first. That didn't affect how many green ones. There's still 6 of them left, but there's only 9 toys. So everybody's okay? What if we've taken a green one out? How many, and our second one is a red? What's that probability? 4 out of 9, and a second one being green? 5 out of 9. Great. So if I want red, red, I want 4 out of 10 times 3 out of 9. And any of these would be an acceptable final answer, right? Whether it's a fraction, a reduced fraction, a decimal, or a percentage, all these are acceptable answers. Keep in mind, though, if you write as a percentage, you got to have that percent symbol on it, because 13.3 is a bonkers number for probability. 13.3%, that's okay. Cool? Joey, is this helping? Yeah, okay. A survey of 1,000 people was performed regarding their gender and whether they were colorblind. Here's our results below. What is the probability that a person chosen at random is colorblind given that they are female? So I'm going to define some letters so I can write a probability statement. So C is colorblind and M is male. So not colorblind will be C complement, and not male, aka female, will be M complement. So we want C given, not M. So that's the probability that of C and not M divided by the probability of not M. So what is C and not M? Two, right? What's the probability of not M? 490. And notice I wrote both of these out of 1,000. Do I really need to write the out of 1,000 though? No, because they're just the out of 1,000 just cancels, right? And I end up with 2 out of 490, or any of those other responses would be okay. You guys good? Okay. What if I want the probability the person chosen at random is a colorblind female? So colorblind and female. Do we know these are independent? No. So we have to assume it's a dependent event. So I'm going to do the probability we're colorblind and, or given that we're not female, or not male, and not male. Everybody's okay? So 2 out of 490, and then not male is 490 out of 1,000, or I get 2 out of 1,000. Now, Mr. Coolett, couldn't I have just said the intersection is this number right here? So I just put it out of 1,000. Yeah. Assuming that these are independent, which they actually happen to be. Was the probability the person chosen at random is a colorblind individual? So I could be colorblind and male or colorblind and female. So 40 out of 1,000 plus 2 out of 1,000, or 42 out of 1,000, which Sam read right away from the chart. Another example. Probability that a regularly scheduled flight depends on time is 0.3. The probability it arrives on time is 0.92. The probability it arrives and departs on time is 0.78. Find the probability that a flight arrives on time given that it has departed on time. So that would be the probability of A given D. So I'll use my formula. So 0.78 divided by 0.83, so 94%. So far, so good. Departs on time given that it's arrived on time. So that's P of D given A. So again, D intersect A, which is the same as A intersect D, so 0.78. Divide by 0.92. So about 85%. How do I check for independence? What if I'm given a situation like this guy here, and I don't know whether these events are independent or not. What if I want to show that something's independent? Well, if an event is independent, if events A and B are independent, then the probability of A given B should just be the probability of A. And the probability of B given A should just be the probability of B. Does that feel good? Or you could check the probability of A and B is just the probability of A times the probability of B. Any one of these three checks will show that we have independent events. So let's go back to this flights question. So let's check to see if arriving on time and departing on time are independent. So three ways we could check this. One is I could check if the probability of A is equal to the probability of A given D. So I did this calculation previously. We got 0.94. The probability of A is given to us in the problem is 0.92. Are these independent? No, not independent. Or I could check if the probability of D is the probability of D given A. We calculated this number previously, it was about 85%. The probability of D is given to us in the problem, it's 83. Are these independent? No. Or the third thing we could do is I could check to see if the probability of A and D is just the probability of A times the probability of D. So probability of A times the probability of D, I get 0.76, which is not the given probability of A and D. So I again conclude we're not independent. What do you guys think? Of the three, which one was the easiest one to check? Was usually this one, because I was given all three in the starting of my problem. I didn't have to do any additional calculation to check it. You know what I mean? All right. In a certain country, the police stop drivers on suspicion of drunk driving. When stopped, drivers are either given a breath test, a blood test, or both, or neither. Records show that 81% of drivers are given breath, 40% are given blood, 25% are given both. What is the probability that driver is given a test? Yeah, let's draw a Venn diagram to start. That would help, right? Specifically, because I know that these are not mutually exclusive events. What word in this problem tells me that? Both, right? When I hear both, usually a good indicator that it's not mutually exclusive. So I drew this. So in my blood circle is 40%. My breath circle is 81%. The both circle is 25%. So what's left to put in blood only? 15%. What's left to put in breath only? 56%. If I add these up, what's left to go in neither? 1 minus 0.15 minus 0.25 minus 0.56 is 0.04. Good job. Sometimes guessing can't underestimate it, huh? So we get a test, any test is 96%. Everybody's good? Okay. Alternatively to doing this, you could have done 0.15 plus 0.25 plus 0.56. You do it that way too instead of doing this formula. The probability the driver is given exactly one test. So that would be the probability of blood only or breath only. So this one plus this one, 71. Right. Everybody's okay? Probability that we're given no test. Yeah. Are the events blood test and breath test independent? Better check it, right? So we'll do the intersection one. We want to check to see if the probability of breath and blood is equal to the probability of breath times the probability of blood. What is this number? Good, 0.25. And what is breath? 0.81. What's the probability of blood? 0.40. So what do I say here? Not independent. Everybody's agree? Which is probably not surprising. You'd think that if you're intoxicated enough to get one, you might get both, right? All right. I think this is my last example. The diagram shows a target for a game. The radius of the board is 40 centimeters and is divided into 3 regions. You score 2 points if you hit the center, 1 point for the middle white region, and 0 points for the outside region. What's the probability of scoring a 2 in one attempt? We should add one other thing, that you can assume that every thing you throw at the target hits the target somewhere, right? You never miss. Be the area of the, I don't know, baby puke circle divided by the total area, right? So the radius here is 10, so pi r, or pi 10 squared divided by pi 40 squared, or 100 out of 1600, or 1 in 16. Everybody cool? Probability of scoring a 1. How do I calculate the area for this white disc? Or I should say washer shape. Nope. It would be the area of this whole section minus the baby puke circle divided by the big circle. Right? So pi 20 squared minus pi 10 squared, and then divided by pi 40 squared, so 3 and 16. Oh my God, this still keeps on going. I got one more. I got more examples. No, I'm not. All right. So this is, I want to cover some of these at least at most situations, because these guys are your prime candidates for using the complement rules, because you can run into some really lengthy counting exercises if you're not careful. So our situation, suppose the probability of there being rain on any given day is independent of there being rain on the day before or the day after. Over the next 4 days, you determine the probability that it will rain on any one of the days is 30%. What is the probability of it raining on day 1 and on day 2? They're independent, so it's day 1 and day 2. So 0.3 times 0.3. Mental math is hard. Is that okay? Okay. How about day 1 or day 2? Nope. So it'd be probability of day 1 plus the probability of day 2 minus the probability of both. So 0.3 plus 0.3 minus the 0.09 from before. 51. So far, so good. Now is complement rule time. What's the probability of it not raining on any given day? Right. So on any single day, the probability of it not raining is 70%. Everybody's okay? Okay. What is the probability of it raining at least once? At least once. So it could rain one time. How many different ways could that occur? 4, right? Could rain on day 1 only, rain on day 2 only, rain on day 3 only, or rain on day 4 only. How many different ways could it rain on 2 days? 4 different ways. 1 and 2, 2 and 3, 3 and 4, 1 and 4, 2 and then 2 and 4, right? You're like, oh my God, this sucks. There's got to be a better way of doing this. There is. So what is the complement of at least once? Less than 1, which is 0 times. So let's just do the probability of 1 minus it raining 0 times. Everybody okay with that? How do I calculate it raining 0 times? Well, it's 0.7, right? Blah, 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 blah. We just talked about this not being good. We said that never raining is probably not rain, not rain, not rain, which are all 0.7s. So if I do 1 minus that, that's our good guy right there. Massively easier to do this than figure out how many different ways they could rain on 2 days or 3 days or 1 day even. Like that's a big hassle, right? What is the probability of it raining at most 3 days? What does at most mean? So it means it could rain 0 days, 1 day, 2 days, 3 days. Yuck, right? What would be easier? And then 1 minus the probability of it raining 4. Yep, exactly. Same idea. Everybody cool? And that's the last one. We did it, guys. Oh no. I didn't record it. That's okay. We'll just use first hours. It says it's recording?
Yeah, an hour and 3 minutes.
Oh yeah, it does say that. Hold on a second.